Hey, this is chapter 20. It's about rapid prototyping processes. And these days we call these processes actually as additive manufacturing processes, since these days they are not only used for rapid prototyping, but we also use the resulting products in the final application. So that's why they can also be considered as main manufacturing operations these days. And as you see, you are responsible from all the subsections. Another thing is that I'm mostly working on this type of process in my research. And in our lab, we have several equipment related to additive manufacturing and rapid prototyping processes. So in the lecture hours, actually, I will make some demonstrations about different types of manufacturing operations. So make sure that you attend the lecture and see what is going on, how these machines are producing complicated products. So why do we need to have prototyping processes? Since if you want to produce a part maybe for 100 times, 1,000 times, million times, what do? You first do design. You design and check whether your design is good enough, fine enough to actually uh, give you the desired properties. So for that purpose, before actually jumping into mass production, you produce maybe a single one, two of them, or three of them, and you do it with some specific equipment. Since if you want to produce the actual part, you need to invest lots of money to purchase some high quality equipment, but that may not be actually feasible. So what people are doing is that they purchase actually some rapid prototyping systems like 3D printers, additive manufacturing systems, and with the help of them, they can easily, in some hours, they can produce such difficult parts, and then they check whether this design is actually the size of this design is fine, whether it's functioning properly, whether its shape is okay. So the main actually objective of prototyping is to check the design for size, shape, and functional properties. And if that is fine, then later, if you want to produce actually millions of them, then you can invest money and purchase some other equipment so that in shorter time you'll be producing thousands of the same product. And you can see some prototypes manufactured with using some rapid prototyping systems, 3D printers, and we'll be discussing all these in this chapter. So what are the advantages of such systems, rapid prototyping systems? Actually, we began to use these technologies in 1980s. Actually, the first rapid prototyping system was invented in 1984. It was the stereolithography system. We'll talk about again the details, and I will also show an stereolithography system to you during the lecture hours. People were using such systems to check the designs. Since the computer software were not that powerful, they want to see the actual product, and for that purpose, they invented such systems. And on the other hand, as I mentioned at the beginning, in addition to using these machines for rapid prototyping purposes, we can also use the resulting products as the final products. And this is called as sometimes direct prototyping or direct manufacturing or digital manufacturing, since it's not anymore a prototype, it's the final product. And on the other hand, we may also be using them for tools. For instance, in your casting operation, let's say, you may prepare patterns by using additive manufacturing or rapid prototyping technologies. If that is the case, then the process itself is called as rapid tooling instead of prototyping, since the resulting product is not a prototype, it's a tool which is going to be used in the manufacturing process. So what type of actually rapid prototyping processes do we have? We have subtractive processes. These are very similar to the machining and other type of manufacturing operations. Then we have additive. Actually, the second one is the main focus of this chapter. Additive manufacturing methods are being used to manufacture such prototypes. And in the additive, as the name implies, actually, we will be adding materials on top of each other to obtain the final product. And as the name implies, once again, in the subtractive type of manufacturing operations, we are obtaining the final part by removing particles, removing chips from the initial workpiece. And the third one is, as the name implies again, is virtual prototyping. We don't see the physical part, but since these days we have powerful CAD software, CAM software, computer software, so with the help of them, we can visualize the actual system and check their functions, check the sizes, and have some comments on them. And then later, if you are done with all these simulations, analysis on computer software, then you can do actually some manufacturing. And you can see some types of additive manufacturing methods or additive rapid prototyping technologies, and we will be discussing most of them in this chapter, and I will be showing you some of these in the lecture hours. And I'm not going to spend too much time on subtractive manufacturing processes, subtractive prototyping processes. They are just machining type of processes like milling, turning, grinding. These can be considered as subtractive processes. And the thing is that if you are going to manufacture a prototype by using subtractive processes, then it's better you use some soft materials like foam or wax or polymer, so that by using simple tools, simple cutting tools, you can at least manufacture the shape, manufacture the final product. But in reality, it may be made of actually steel. But if it's a prototype, then you shouldn't be consuming actually steel or other difficult materials. Instead, you should use such wax, foam, or polymer materials, so that the manufacturing can be completed in a shorter time, and you're not going to spend too much money on the material. Now we will be actually discussing some types of additive manufacturing technologies which can be used for prototyping purposes and as well as for direct manufacturing purposes. You see, we have several methods: fused position modeling, stereotypography, multi-jet, selective laser sintering, electron beam melting, laminated object manufacturing. There are many of them, beam deposition methods, and there are many, but in this textbook, actually, we are going to just discuss these. And if you are interested, we can do a quick search and see that there are other also additive manufacturing type of processes. And this is the first one, the first type of actually process we are going to focus on. It's called fused position modeling. By the way, this is a trademark name, and these days we prefer to use the term fused filament fabrication, but they refer to the same technology. Now I will show you the fundamentals of this machine. So it was first invented by actually the company called Stratasys. So this is an example of their system, but at the heart of this machine, what do they have is that this is the basic of the process. So what do we have? We have a table, and the product is actually manufactured on this table. This table is moving in Z direction, and then we have actually a kind of an extruder. The tip of this actually extruder head is heated so that the fat material, the material is in the form of filaments. As you see, we have a roll of filament, and this is supplied by using a kind of an step motor, so that stepper motor, and once it's actually fed into that nozzle, its temperature is increased, its state becomes semi-solid, and then with the help of this extrusion process, it's actually a simple extrusion process we have seen in the previous chapter, in chapter 19. And then once this actually material is extruded, it moves over the table and deposits material onto the table or onto the previous layers. So we need to have a proper trajectory. And how do we obtain these trajectories? It's actually summarized in this sketch here, in this figure. We have a kind of a pipeline, and we need to follow some steps to perform this manufacturing operation. So how do we start? We start with an STL file, STL design file of our part. Assume right now that this is the part we are going to manufacture. So what we do in the second stage, we do slicing. In additive manufacturing process, in almost all of the additive manufacturing technologies, we produce these parts layer by layer. So we produce the first layer, deposit material for the first layer, and then start producing the second layer, and then the third, fourth. This goes on like this until you are done with the part. And you see, if you look at the top view of a slice here, probably it's something, I think, at around this zone, around this height. So you see we have these two kind of towers here. Probably it's around this height. So you see, we are not just going over the contour of the slice, we also actually deposit material inside this contour. And that's an important issue. Depending on your settings, you may fill it completely, you may have 100% infill, or you may have 20%, or just keep this actually interior empty. It's up to you. You may just have the shells. So these outer contour is called as shells. And if you look at it carefully, we have two shells, and in the interior part of this slice, actually, we have a kind of a zigzag pattern. It doesn't have to be zigzag, but there are different ways to fill these interior. And another issue is that since we are adding these materials layer by layer, and at some points, once you actually extrude material, there may not be actually any support underneath. For instance, think about such an L shape and reverse L shape. If you take slices, there is no problem up to this point. But if once you are trying to manufacture this slice here, you can see that there is nothing underneath. But if you are depositing material, obviously it will not stay at that level since we are not supporting it underneath. So that's why in such critical overhanging regions, what we do, we make use of support structures. So this is actually represented here by using gray or black color here. And you may use the same material for the support structures generation, or use different materials. You may even use some water-soluble support structures, so that once you manufacture actually complicated parts, you can simply put your part into a kind of an water pool, and if you wait for some time, then later these support structures will be dissolved, and you will be left with just the desired part. You will be just left with the blue part. So if you get all these trajectories actually, and then what do, you transfer these trajectories to the machine. So, and this machine actually accepts some G codes, which are very similar to G codes we are using in CNC type of machining operations, very similar to them. And once you actually transfer these G codes onto the machine, then the controller of this machine actually parses all these G codes, and then extrudes material onto the table, onto these actually previously printed layers, or onto the initial layer. So it follows like that, and once you are done with all the layers, you'll obtain the desired product. Another thing is that for different type of materials, we may need to have a heated bath. For some specific plastic materials, the bed temperature is usually set to 60 degrees, 80 degrees, maybe sometimes to 100 degrees for difficult plastics, but usually it's set to 60 degrees for polylactic acid type of material. And as I said, I will be showing you the CAM software of this type of machines, and also I will make a demonstration on the machine. So I'm not going to spend more time on this. Maybe I may talk about the support here. You can see some overhanging regions. So this is a letter T, and if you want to print in this orientation, then what will happen once you're at this level and extrude material, you will see that there is nothing underneath. So for that purpose, before starting the manufacturing process, your CAM software should be aware of this problem and generate some support structures underneath. You see, we have such a support structure underneath. With the help of it, with the help of the quality of the underneath surface, and the quality of the part is improved. Another shape here, as you see, if you are trying to manufacture in this orientation, then you need to use such a support structure underneath. But obviously, there are other ways. Instead of printing this part in that orientation, what I will do, I will just rotate it 90 degrees and print the same product without using any support. So I can say that the orientation of the product is highly important. By adjusting your orientation, you may print the same product without using support structures. Then we have the second type of actually manufacturing, additive manufacturing process is called as stereolithography. By the way, it is the first type of additive manufacturing invented in 1984 in Japan. What we do in this process, we make use of, first of all, thermoset type of plastics or resin type of plastics. They are not in actually solid form at the beginning of the process. At the beginning, it's in liquid form. By the way, I forgot to tell that in this process, in FDM, fused filament fabrication or fused deposition modeling, we make use of thermoplastic type of filaments, and they are recyclable. So once you're not happy with that part, you can easily recycle it and again change it into a form of filaments. But it's not the same in thermoset type of plastics. They are not recyclable, since what we do in this process, we change the state of this material by using UV light. So initially in the process, we start with a pool of liquid material. This is, as you see, we have a vat, and this vat is filled with actually liquids or polymer thermoset material, or we can call it actually sometimes as resin. And then what happens, we make use of some light sources. They may be kind of laser, they may be some different light sources like projectors, even simple light, so that once you actually apply this light on the resin, what will happen? We will start some chemical processes. This liquid, actually thermoset material, will start a polymerization process. Since inside this actually liquid material, liquid resin, what do we have? We have some amount of monomers and we have some amount of photoinitiators. So once the amount of energy is high, once you apply too much light on this resin material, and then the photoinitiators will start the reaction. Once the reaction is started, we will have monomers actually forming some chains so that they will be connected to each other. And once this process is done, once polymerization is done, we will not have any more liquid material, but they will be solid, and this is called as photopolymerization. And in stereolithography system, what we do, we make use of this main principle of photopolymerization. And what about the rest? So how we manufacture complicated products? So at the beginning of the process, this platform is at the top of this vat. So we have little liquid material at the top, and then with top of our light source, again, our light source moves as in the case of actually FDM technology. But for most of the systems, if you are using a laser as a light source, instead of actually moving the laser, what we do, we make use of mirrors. We just rotate the mirrors so that this light, the laser beam, is actually transferred onto this top surface of the vat, and these polymers are actually polymerized, and we will have solid objects. And then once this one layer is actually polymerized, we simply move this platform a little bit down and then polymerize the second layer, move it a little bit more, polymerize the third. So we go like this and until the part is ready. And again, for overhanging regions, it's not shown here, but for the overhanging regions, again, we need to have some support structures, like in the case of fused deposition modeling. Just the difference is that the type of support structures are a bit different. In stereolithography systems, we prefer to use some tree-like support structures. So instead of accordion-like support structures, we make use of tree-like support structures. And then later, once this product is actually over, what we do, we take it from this pool, clean it by using some alcohol, isopropyl alcohol, IPA, and then later, if you are not satisfied with the strength of the product, you may put it into a kind of an oven and do extra curing operation. By the way, this actually polymerization is sometimes also called as curing, since this liquid is in the form of resin, and we are curing this resin. So they are also called as curable liquid or curable resin. Then we have another process called as multijet or polyjet modeling process. It's somehow similar to stereolithography. The difference is that instead of using an vat of resin, what we do, we have an actually hat, and in this hat, I will show you some example videos. In this hat, we are jetting some photopolymers, and then once these polymers are actually hitting the surface, they are polymerized with the help of UV light, which is actually embedded onto the hat. So they are acting as a kind of a light source. So without using a kind of an liquid tank, we will be manufacturing such products. And as I said, I will be showing you some examples. The layer thickness is very low in this process, it's about 16 micrometers. Then we have selective laser sintering, and this process mostly used for polymers like polyamide type of plastics, but it's not highly used for metallic powders. For if you are going to use metal powders, then you should use selective laser melting instead of sintering to make actually process a bit better. This is preferred, but in selective laser sintering process, we make use of powders. So the powders we were using in the powder methodology can also be used in this process. So how we do, this is a nice schematic of the selective laser sintering process. This is the process chamber you see. We have two cylinders. So the first cylinder is responsible for feeding the powder, and the second cylinder is responsible for the manufacturing of the part. So what happens at each layer, this powder feed cylinder actually goes up a little bit, which means that it's actually moving lots of powders onto the table. And then we have a roller here. So with this roller, the powder is actually spread on this part build cylinder. So we can assume that this is a kind of a table. So with the help of this roller, the powder is actually carried to this right hand side. And right now, assume that on this right hand side, we have a thin layer of powders which are not processed yet. And then later what we do, according to the slice of your part, this laser is actually reflected on this plane, and these powders are sintered. So they are fused together with the help of the energy of our laser. And as you see, this laser is fixed, it's stationary, and we have some galvanometers here. And inside these galvanometers, we simply have some mirrors, and we are simply rotating these mirrors so that the laser beam is actually reflected on any point on this plane. And once all these actually regions are fused together, once all these powders are fused together, and then later what we do in the next layer, we move this build cylinder about one layer thickness, and then again this powder field cylinder will go up actually about one layer thickness, and then roller again will spread the powder. Then again these powders will be fused together with the help of the laser. So this process will go on until you are done with the process, until you are done with the part. So at the end of the process, our product actually will be printed inside a kind of an actually powder bed. So we have a powder bed, and at the center of this powder bed, we have our 3D product. And the advantage of this process is that you don't need to use support structure, since the powder underneath the overhanging regions will be acting as support structure. So this is a nice property of the selective laser sintering process. And additionally, this chamber is highly important. We need to control the humidity, temperature, and also the pressure there. We may be using some inert gases in the chamber so that the process can easily be controlled. We will not have any excess sparks, and the quality of the resulting parts will be a bit better. And in order to actually decrease laser power, we may also have some extra heaters inside so that the powders may be increased to some temperatures first, and then with the help of the laser, their temperatures may be improved a little bit more. So that by using less laser power, we can do this same process. And I will again show you an example of this process in the lecture, so I'm not going to discuss anymore. Then we have electron beam melting process. It's somehow similar to selective laser sintering, but the difference is that we will be using an electron beam instead of laser. And another difference is that this chamber should be in vacuum atmosphere. So we can only perform electron beam melting process inside a vacuum. If you remember this process, we said that it should be always performed in vacuum atmosphere. In other cases, we will have problems. We may have some wires, sparks all generated. So that's a must for electron beam type of operations. Then we have another similar process. It's called as three-dimensional printing. It's sometimes abbreviated as 3DP. And this is summarized here. By the way, it's actually this was invented by MIT, Massachusetts Institute of Technology, but obviously these days the patent has expired. You can even start manufacturing the same machine on your own. So what are the differences? This time, again, we are using a powder bed, but the difference is that instead of a laser, we are using a kind of a hat, and it's depositing binders. You see, binders are deposited onto the table, and with the help of it, the powders are fused together, joined together, but the rest is the same. As you see, we have a roller is spreading the powders, and after one layer is joined, then our piston is going downwards, and we go on like this, and at the end this will be the last layer, and once the process is over, you can simply take your part out of this powder bed. But the thing is that you need to do some extra operations. In this process, secondary operations are must. And what are these? First of all, you need to remove these binders first, and this is called as actually burn-off process. Once the process is over on this machine, we will have such a kind of an actually microstructure. You see, we have metal powders. You can also use ceramic powders or different type of materials, and in between these metal powders, as you see, we have binding materials. So in the next stage, we need to remove these binding materials, binding agents, and then later, in order to fill all these porous regions, like in the case of powder metallurgy process, actually, we do some infiltration. And as you know, the infiltration is done with the help of a material having a lower melting point temperature than the melting point temperature of the original material, or in our example, the metal powder here. This is a very nice process, and there are some companies working on this technology. Again, I will show you some example videos from X1 company. They can even use sand powders. Sand particles are used to manufacture actually some molds for casting operations. So I will show you a nice video about this process. And by using such technologies, we can produce highly difficult products, as you see, very small figures, such kind of figures from World of Warcraft, as you see, and they can even be colorful by using some multi-jet type of 3D printers. Then we have another type of additive manufacturing technology. This is called as laminated object manufacturing. We sometimes use the term LOM, and this is highly different with respect to the previous ones. And in this process, we mostly use paper or sometimes PVC type of material. So we start with an roll of actually material. As you see, this is continuously supplied to this side, and at the other hand, at the left hand side, we have a take-up roll. So the remaining part of the roll is actually wind up actually over this one, and the main manufacturing operation is actually performed on this table here. So what is on here? Again, this is a layer by layer process. So on the CAM software, we obtain the slices, and then with the help of this laser system here, the contour of that slice is actually covered with the help of the laser, so that the paper is actually cut, and you don't need to use, by the way, a laser. You may also use a kind of a knife, a mechanical knife, so that these contours can be cut into that shape. And another thing is that the remaining part of this paper is actually divided into some squares, as you see, and this is done for all layers, so that once the product is over, once the manufacturing is over, we can easily remove these cube shapes from the outer side of our original product, and it will be easier for us to obtain the final product. Otherwise, since it's a kind of an box shape, and it will be quite difficult to remove the desired product from that kind of an paper, let's say paper bed. And you see this a nice example, a very complicated shape. This was manufactured by using such a technology. Then we have laser engineering net shaping. This is actually not complicated what we use. We use kind of sometimes powders or wires, and we are using the high power lasers in this process. We deposit them on the table or onto the previous layers and try to join with the previous layers. But obviously, this is quite difficult to control, since if you are using powders, you may have some powder spread on the table on the previous regions, previous layers. So this is a quite difficult process, but there's a trademark. It's called laser engineered net shaping. Even though it's called as net shaping, you may still need to do some extra finishing operations. And the virtual prototyping, as we discussed at the beginning, is not complicated. These days we have powerful CAD software, powerful computer-aided engineering software. So with the help of them, without fabricating the real product, you can see whether your product is functioning properly, whether its properties, mechanical properties are fine. So you can easily understand it by using such powerful engineering software. Then we have a brief discussion about self-replicating machines. If you remember, I said that these actually additive manufacturing things started around 1984 and 1989. We have two main patents. One of them is about stereolithography. It was in the year of 1984, and the patent of FDM was granted in 1989. So after 20 years, these patents were expired. So what people have done is that they actually start a kind of a forum, and their motto was to manufacture a 3D printer which is capable of printing itself. So that's why we called such kind of actually approaches as self-replicating machines, since we have a 3D printer, and this 3D printer can print the product, prints the parts of another 3D printer. So it's self-replicating kind of a machine. And with the help of these approaches, hobbies, actually, the price of these FDM systems decreased tremendously, since before the patent was actually expired, the price of such printers were about $100,000, but these days we can even purchase them by maybe about less than $200. And as I said at the beginning, instead of just using these processes for prototyping purposes, we also use them as final manufacturing process. Since, for instance, if you are producing kind of a toy, it's not a prototype anymore. You can use it directly, or if you are using high quality plastics or high quality powders, metals, then the resulting product can be used in your final application. So if that is the case, then it's simply called as direct manufacturing. And in addition to these, they may not be final products, but you may be using them at some stage of your manufacturing. And if that is the case, it's called as rapid tooling. We have some examples. For instance, this is a nice example of digital manufacturing. or direct manufacturing. There's a company called Align Technologies in the United States. They are producing such aligners according to the actually properties of each person. So they do some kind of a scanning, and then they manufacture these aligners just for you. And these aligners cannot be used by any other people. And what they are doing is that they produce these aligners every 2 weeks so that they can actually shape your teeth. And this is a nice example of additive manufacturing and direct or digital manufacturing. So you see they are using stereolithography process, and in a single manufacturing process they produce maybe about hundreds of them at a time. But obviously they need to design these properly. Their CAD systems should be powerful enough to manufacture these to actually parts at a time. And then now I will show you some rapid tooling examples. For instance, we haven't seen the casting process, but in the next week we will be discussing some casting processes. You will see that in casting, the patterns are highly important, and we can make use of some additive manufacturing technologies actually to manufacture such patterns, and then later they will be used to obtain the final mold, and finally we will be pouring our molten metal into these cavities and obtain metal products. So you have seen that these parts were manufactured by rapid prototyping systems or 3D printers, but they're not final products. So they are just patterns of the final product, and that's why we call it as an rapid tooling application. This is another example, and again, we make use of rapid prototyping or additive manufacturing technologies to obtain the molds for casting process. These are other examples, and I will show you an sand mold preparation of sand 3D printer during the lectures. So this is actually all for this chapter. Please make sure that you go through the review questions and as well as qualitative type of problems.